In the last video, we talked about this giant box of properties of double integrals, or properties of volumes as we thought about them. And in this video, we're going to take a look at example number 5. We're going to see which, if any, of these properties might be useful in helping to answer a question like example 5. So example 5 says, suppose that the region D is a region in the xy plane, and it's bounded by the curve x equals y squared and x equals 4. Can I use a double integral to determine the area of D? Okay, so right off the bat, we might recognize which property is going to be useful here. We're asked to find the area of a region, but we want to do that using a double integral. Well, that should very simply then correspond to property number 5. So we're going to go ahead and see that if we were to just do a double integral over D of 1, then that should represent the area of my region D. Okay, but I'm still going to need to go through the same standard steps in order to set up this double integral. Notably, I'm going to have to think about what the region D looks like and define it. So I'll say here, we sketch a picture of D. And let's see, this is going to be x equals y squared is a sideways facing parabola. And x equals 4 should just be a vertical line. And so my region D should be right here. Everything that's bounded by these two curves. Okay. And I need to think about how to define D. So I'll say we define D to be equal to a bunch of points x comma y such that, and now I need to think about if I want to view D as having a top function and a bottom function bounding it, or if I want to see it as a left function, right function. In this case, I actually think it's easier to imagine it as a left function and a right function. If I was in the region and I was anywhere in the yellow and I always walked to the right, the function that I would always bump into would always be 4. I always hit x equals 4 all the time. And if I was inside the region and I always walked to the left, I would always be bumping into that parabola that is the y squared. And once I have that, I can easily then figure out the bounds here on y. I would really just need to figure out how low and how high my y values can go here. But I'll notice that if x is equal to 4, the parabola should go all the way down to heights of -2 and all the way up to a height of +2. So this would be a way I could define D. And again, it's totally legit if you wanted to define it with a top function and a bottom function. If you wanted to do that, you would have to solve this equation to be y equals, and you would get plus or minus the square root of x. Notice that the top half of the parabola would be the positive square root, and the bottom half would be the negative square root. And those would be what you would need to bound y. I'm just going to go ahead, though, and set up my area here using the definition of D that I've already gathered. All right, so we know by property number 5 up above that I really just want to be integrating the function 1. And if I am going to do that, notice that I should then set up the integral y squared to 4 and -2 to 2, 1, and then here I would have dx dy. Okay. Evaluating this then should be really simple. In fact, the first integral is trivially easy because I'm just integrating 1. So notice I should get to -2 to 2, and then I'll just get, let's see here, I get x as my antiderivative, and I have to evaluate that from y squared up to 4, and then I put a dy here. So if I simplify that up a bit more, this is going to be 4 minus y squared dy. And now I just integrate this with respect to y, and that should also be rather simple. I'm going to get 4y minus a third y to the third, and I just evaluate that from -2 to 2. So let's see, that's going to be, if I plug in 2, 8 minus, looks like 8 thirds. And then if I plug in -2, I'm going to get -8, and it looks like plus 8/3. Okay, so if I was to simplify all this up, I end up with 16, looks like minus 16/3. If I distribute my negative here, I get plus 8 and minus 8/3. So yeah, negative 16/3. 16 times 3 is going to be 48/3. Take away 16/3 should leave me with the final result of 32/3 as the total area of the region. So again, all we did here is we just did a double integral to calculate the area of a region. Now, there's one important thing to kind of note here, something that's actually kind of cool. You know, back in Calc 2, one of the things that you would have talked about is this idea of how you find the area between two curves. And of course, back in Calc 2, we didn't have double integrals, and so we would have asked a question very much the same as this one, except we would have said use an integral to find the area of D. Just a single integral. And you might recall that in Calc 2, we would have set this up by thinking about our region as having a left bound and a right bound, and then we would integrate with respect to y. Or we could have seen our region as having a top bound and a lower bound, like a top function, bottom function, and then we would have integrated with respect to x. So in this case, we would have maybe imagined the region like this. We could have imagined like approximating rectangles moving across it in a horizontal fashion. And so we would have thought maybe about this region as having a left edge and a right edge. And so in Calc 2, we would have said that the area here would have been equal to a single integral of right function minus left function. We would have been integrating with respect to y because our approximating rectangles stacked vertically, as you can see here. And the lowest possible red rectangle would have been down at -2, and the highest would have been up at +2. But take a moment here to think about how this Calc 2 setup relates to the Calc 3 setup. Isn't it actually the case that this integral right here appears in our work from up above? Like, isn't it exactly the same as what we have right here? This is actually what's so cool about this idea of a double integral helping us set up and find the area of a region. It's really just kind of an extrapolation or a generalization of the ideas that we covered in Calc 2. So we can then obviously say here that this should just evaluate out to be the exact same area of 32/3. And so we have a way to think about this using Calc 2 and a way to think about this using Calc 3 as well. So next time you're ever maybe, I don't know, going back and looking at some old Calc 2 stuff, helping a student through Calc 2, or need the area of a region, you can note that there's actually kind of two ways that we can think about doing it.